Hey guys, welcome to our first video on the 4 transformations of shapes on graphs. So in this video, we're going to run through a quick recap of each of the 4 different types of transformation. And we're also going to mention something new to GCSE called invariant points. So with transformations, we really need to know how to perform the transformation and also how to describe the transformation when it's already happened. So each of the 4 transformations, translation, rotation, reflection and enlargement, each of these will at least get 2 of their own videos. The first of which will probably be on performing the transformation, the second of which will be on describing the transformation when it's already happened. So I'm probably going to start on enlargement first of all, because that seems to be the guy that causes the most problems. So there will probably be quite a few videos on enlargements. And as we go, we're probably going to mention invariant points in each video. So let's get cracking then. Let's have a quick little run through on each of the 4 transformations. Okay, first up then, probably the simplest of the 4 is translation. So all that translation does, it moves a shape left or right and up or down. So it doesn't change the shape at all, it just moves the shape. And translation is done by a vector that looks like this guy. So here we have a column vector. So our top number in these column vectors is our x vector. If this number is positive, then our shape moves to the right. If it's negative, our shape moves to the left. And the bottom number in our vector is the y vector. If that's positive, our shape moves up. If it's negative, our shape moves down. So let's take a look at an example. Okay, so here we have quite a simple example of translation. How has shape A moved to shape B? Well, all that we would do for this, we would count how many squares to the right and then how many squares down. So I would always recommend picking a point on your shape. So as I have done here, on shape A, I'll put a little cross and then find that corresponding point on the transformed shape and then just count how many places has that moved to the right and then how many places down. So here it turns out the shape has gone 13 places to the right. So our x vector is positive 13 and then it's moved 1 place down. So our y vector is minus 1. So our translation vector is 13 minus 1. On the flip side, if we wanted to get back to shape A from shape B, we would have to do the exact opposite. So we would have to go 13 places to the left. So that would be minus 13 and we would have to go 1 square up. So our y vector would be positive 1. So the vector minus 13, 1 would take us back from shape B to shape A. Okay, transformation number 2 then, we're looking at reflection. So reflection basically mirrors your original shape through a mirror line. So the result you end up with is always a symmetrical picture about the mirror line. So if we take a look here at how A has reflected to B, well, again, if we pick a point on shape A, so I'm going to pick this point here, if we count how many places that is away from the mirror line. So here it's 2 squares. So to reflect that point in the mirror line, we go 2 squares to the right of it. So the arrow tip reflects to that point there. So we can do that with every other point on the mirror line from the original shape. So if we were to look at this point here, then that is 3 places away from the mirror line. So it reflects just to the right, 3 places away from the mirror line on the other side. So reflection can get a little bit trickier when you're reflecting in a diagonal line, but we'll take a look at that in reflection's own videos. Okay, on to the next. Okay, transformation number 3, we have rotation. So rotations, yeah, they can be a little bit complicated. We've got quite a bit of information with rotations. So first of all, a rotation moves the shape and it also spins it or rotates it, hence the name. So rotations are usually carried out about a certain point called the centre of rotation. So depending on where your centre is, your shape is going to be in different places after the rotation. Rotations are either clockwise or anti-clockwise, and they will either be 90 degrees or 180 degrees. So the reason for that, if we said we were rotating a shape 270 degrees clockwise, that's exactly the same as rotating a shape 90 degrees anti-clockwise. So we really only worry about 90 or 180 degrees. So let's take a peek at an example of rotation. Okay, so here I've actually carried out 2 rotations on shape A. So we've done one to turn it into shape B and one to turn it into shape C. So let's take a look at each one and talk about what the rotation is. So A to B, first of all. First of all, I've rotated it about centre 0, 0. So the origin. So the centre is 0, 0. Okay, so we can see the shape has gone from being in the top right quadrant to being in the bottom right quadrant, and it's also flipped from being on its short end to being on its long end. So this has been a rotation by 90 degrees, and then we also would need to say what direction it's gone in. So it's happened in the same direction, hands move around a clock, so it's clockwise. So A to B is a rotation of 90 degrees clockwise, centre, the point 0, 0. Now the transformation of A onto C is very similar. So again, it's a rotation by 90 degrees, centre 0, 0, 90 degrees. This time it's anti-clockwise. So I'm just going to say ACW, anti-clockwise. So that's an example of 2 rotations there. Again, we'll go into far much more detail in rotations own videos. So that leaves us with one more transformation to take a peek at. And it's everybody's favourite, enlargement. So, bizarrely, when we do enlargements in maths, we are either making a shape bigger, that makes sense, or enlargements can also make a shape smaller, believe it or not. So obviously in real life, if you enlarge something, you'd always be thinking about making it bigger. In maths though, when you enlarge a shape, you can also make it smaller. So the resulting shape you get from carrying out an enlargement is always similar to the original shape. That's worth noting. So enlargements are carried out by a number called a scale factor. So a scale factor is simply a number that you multiply the lengths of the original shape by to get the new enlarged shape. So enlargements are usually carried out very similarly to rotations. They are usually carried out about a point called a centre of enlargement, but sometimes you are actually just asked to enlarge a shape by a scale factor with no centre. So we'll take a look at 2 examples with enlargement, and then we will look at many more examples in enlargement's own videos. Okay, so first up we'll take a look at an example without a centre. So first of all, let's take a peek at A. So A has a base length of 2 and a height of 4. So what we're doing in this example, we are enlarging by a scale factor of 2. So all that we need to do with these 2 lengths that we've got, we multiply them by 2. So 2 times 2 is 4, and 2 times 4 is 8. So our enlarged triangle is going to have a height of 8 and a base length of 4. Now we don't need to worry about the diagonal length, that will take care of itself once we enlarge the other 2 lengths. So here is shape B. So as we said, he's got a height of 8 and a base of 4. So what we've done, again, we've enlarged triangle A with a scale factor of 2 with no centre of enlargement, and that has given us triangle B. So triangle B could be anywhere on this page that we want it to be. That's the important difference between having a centre and not having a centre, is that a centre strictly dictates where the enlarged shape goes. When there's no centre, it can go anywhere it wants to. Okay, cool. Okay, so now let's take a peek at an enlargement with a centre. So what's happened here? Triangle A has been enlarged with a scale factor of 3 to give us triangle B, but this time it has happened about a certain point, P. So let's zoom in and take a peek at what has happened. So P is the bottom right corner of the triangle. Now if we're enlarging with a scale factor of 3, we need to multiply the lengths of triangle A by 3 to get the length of triangle B. So what we've done, 4 times 3, and that has given us 12, and 2 times 3, that has given us 6. So those are the base and the height of triangle B. But why have we drawn it as we have? Well, when we have a centre of enlargement, as we do here, the distances of points away from the centre increase by the scale factor. So, for example, if we look at the base, well, the bottom right tip of triangle A was 2 places away from point P. Now if we multiply 2 by the scale factor 3, we get 6. So this point over here is now 6 squares away from point P. So the distance of the original point has increased by a multiple of 3 away from point P. And then very similarly, the tip of the triangle A was 4 squares above point P, so that increases by a multiple of 3. So 4 times 3 is 12. So now the enlarged point, or the enlarged tip of the triangle, is now 12 places up above point P. Now this is the only place that triangle B is allowed to be because it is enlarged around this point P. If P was in a different place, then triangle B would be in a different place. Again, we're going to go through a lot more of these in much more detail in Enlargement's own videos. Okay, so now we just need to talk a tiny bit about what an invariant point is. Okay, so the good news is invariant points are incredibly simple. They're pretty much what they sound like. So an invariant point is any point on a shape that does not move during a transformation. So different transformations have a different amount of invariant points, and it also depends on where our mirror line is and where our centres of rotation and enlargement are too. But we will either talk about invariant points more in each video, or we'll have a video dedicated to invariant point questions. Haven't made my mind up yet. If we look at this previous example, where we enlarge triangle A with a scale factor of 3, centre the point P. Let's talk about the invariant points here. So, well, what's happened here? Well, we're enlarging with a scale factor of 3 with reference to a point P. So every single point on this triangle has actually got further away from point P, except with one exception. Now the one exception is at point P itself. The point P is 0, has a distance of 0 away from itself. So when we multiply a distance of 0 by a scale factor of 3, we still get 0. So point P itself is the only invariant point when we've carried out this transformation, because the bottom left of the triangle is still the bottom left of the triangle after we have carried out the transformation. So point P is invariant. In contrast, if we were to talk about this point here, this point has varied, it's changed. This point has transformed to this point. So it's not invariant, it has varied. And that's true of any other point anywhere else on the triangle. It is only at the point P where we have an invariant point. So that is what an invariant point is. It is just a point that does not move under a transformation. So I should say here as well, one transformation never has any invariant points, and that is translation. When we're carrying out a translation, remember what we are doing. We are moving a whole shape, left or right, up or down. So every single point on a shape moves under a translation, so there are no invariant points. Okay guys, so that's a quick little skim over our 4 transformations and an introduction to invariant points. Now it's time to go into them in much more detail, and I'm going to start with enlargements because they seem to be the ones that everybody hates. Remember, if you found this video helpful, please don't forget to subscribe to the channel, and also leave us a cheeky thumbs up, and leave a comment down below the video telling me how you found it. Cheers guys!